You trust your car's brakes without even thinking about them. You press the pedal, the car stops. Simple. But right now, somewhere on a highway near you, a 40-ton machine that's like stacking around 30 average cars is coming to a stop using air. Yes, actual air. The same thing you're breathing right now. So why would engineers design something like that? What happens if the air runs out? Why don't regular cars use this system too? And what's that loud shh sound you hear when a parked truck releases pressure? Here's the interesting part. Most people hear that sound and assume something's wrong. In reality, it's the truck actively making itself safer. Let's rewind a bit. Your car's braking system works a lot like a giant syringe. When you press the pedal, it forces brake fluid through lines, and that pressure pushes pads against a spinning disc to slow the wheel down. Simple. Apply pressure and the car stops. For smaller vehicles, this system is excellent. Lightweight, affordable, and highly responsive. But when you scale that same idea up to a fully loaded 18-wheeler, things start to break down in ways most people don't realize. A common assumption is just use bigger pipes and more fluid. Bigger truck equals more fluid equals more stopping power. Sounds logical, right? But that exact thinking can be dangerous. Here's why. A truck would need hydraulic lines running the entire length of the vehicle, sometimes up to 70 feet, across multiple axles, exposed to harsh weather and constant road stress. If hydraulic fluid leaks at any point, that axle can instantly lose braking power. No warning. No backup. Engineers call this a fail-open system. If something goes wrong, the brakes stop working. Now here's where it gets really interesting. Air brakes work the complete opposite way. If the system loses pressure, the brakes don't release, they automatically engage. The truck brings itself to a stop. This is known as a fail-safe system, and it changes everything. So how does it actually work? The truck's engine powers a compressor, basically a pump, that continuously pushes air into storage tanks mounted along the truck's frame. Those tanks store air at around 100 to 120 pounds per square inch, about the same pressure as a high-performance road bike tire, but inside a much larger reservoir. That compressed air just sits there, ready to be used at any moment. When the driver presses the pedal, they're really not using their leg to create stopping force. Instead, they're simply opening a valve. The moment that happens, the stored air rushes out and flows into brake chambers, small metal cylinders located near each wheel. Inside those chambers, the air pressure pushes a component called an S-cam. You can think of it as a rotating wedge. As it turns, it forces the brake shoes outwards, pressing them firmly against a large metal drum attached to the wheel. The resulting friction brings the truck to a stop. So in reality, it's not the driver's leg stopping a 40-ton machine, it's the power of compressed air. And that's the game-changing difference. In a car, pressing the pedal creates the force needed to stop. In a truck, pressing the pedal simply releases force that was already stored and waiting. Here's the detail most people overlook. Inside the rear brake chambers, there's also a huge coiled spring. Imagine something about the size of a soup can, but wound incredibly tight. That spring is constantly being held back by air pressure. As long as the air tanks stay pressurized, the spring remains compressed and out of the way. But the moment air pressure drops, whether it's a slow leak, a small line failure, or the driver intentionally releasing it to park, the entire system changes. That tightly wound spring is suddenly free, and when it releases, it forces the brakes on instantly and with serious power. That loud shh sound you hear when a truck parks, that's not a problem. It's intentional. The driver is releasing air from the spring chambers on purpose. As the air escapes, the springs expand, the brakes lock in place, and the truck stays exactly where it is. No malfunction, no leak, just the system working exactly as it was designed to. Now, compare that to your car's hydraulic brakes. In a hydraulic system, your foot generates all the stopping force. In an air brake system, the energy is already stored. The driver simply controls when it's released. With hydraulics, a leak anywhere can mean losing braking power on that entire circuit. With air brakes, a loss of pressure actually triggers the brakes to engage. Hydraulic systems are perfect for smaller vehicles, efficient, lightweight, and cost-effective up to around 5 or 6 tons. But air brakes are built for scale. Whether it's 40 tons or even 80 tons, they handle massive loads while staying safe. So while hydraulic systems win on simplicity and cost, air systems win where it matters most for heavy vehicles: safety during failure. Cars use hydraulics because they don't need anything more complex. Trucks use air because when you're hauling tens of tons at highway speed, what happens if something goes wrong wrong matters far more than keeping things simple. And one more thing that often confuses people. That loud engine roar you hear from trucks going downhill, that's not the air brakes at all. It's something called a jake brake, where the engine itself helps slow the vehicle down using compression. Completely different system, completely different purpose, just another layer of control. Now here's the surprising part. This idea isn't new at all. Go back to the year 1869. A 22-year-old inventor named George Westinghouse is riding on a train when it suddenly has to make an emergency stop. What he sees is chaos. Brakemen are running along the tops of moving rail cars, each one manually turning a wheel to slow down their own car. Imagine trying to coordinate that across a train with 50 cars. The timing is nearly impossible, and accidents are common. Watching all of this unfold, Westinghouse starts thinking. He asks a simple but powerful question. What if a single signal could stop every car at the exact same moment? That simple idea led George Westinghouse to invent the automatic air brake for trains. His design used one continuous brake line running the full length of the train, kept under pressure. The moment that pressure dropped, whether intentionally by the engineer or due to a brake, every car's brakes would activate simultaneously. From the very beginning, it was built as a failsafe system. By the 1880s, after a devastating railway accident exposed how dangerous the old manual braking method was, this system became mandatory across railroads. It completely transformed transportation safety. Fast forward to the 20th century, as trucks began taking over freight transport, engineers didn't start from scratch. They borrowed what already worked. They adapted Westinghouse's air brake concept for road vehicles. So today, every semi-truck on the road is running on a safety principle that's over 150 years old.
You might think this is just a trucking thing, but it's not. You've actually experienced this system your entire life. Every school bus that stops to drop off children uses air brakes. Every city bus that lets out that familiar hiss at a stop, that's the system engaging. Fire engines rely on it because a 40,000-pound vehicle rushing to an emergency can't risk brake failure. Airport tow vehicles use air brakes because losing control near an aircraft isn't an option. Construction dump trucks depend on them for stability on rough, uneven terrain. Massive mining haul trucks, some exceeding 400 tons, even heavier than a fully loaded Boeing 747, use scaled-up versions of the same system. Military transport vehicles, garbage trucks, long-distance buses, fuel tankers, agricultural tractors, and articulated lorries across continents all rely on this same core idea. Even modern railway carriages still operate on the same principle that Westinghouse introduced over a century ago. That hissing sound you've heard countless times at bus stops, loading docks, and roadsides, now you know. It's the sound of a system designed to keep everything safe. Of course, air brakes aren't perfect. They come with their own challenges. The biggest one is response time. Air takes a tiny fraction of a second longer to travel through lines compared to hydraulic fluid. At high speeds, even that small delay matters. For example, a typical car traveling at 60 miles per hour needs around 130 to 140 feet to come to a complete stop in an emergency. A fully loaded truck traveling at the same speed can need around 525 feet to come to a stop. That's almost the length of 2 football fields. That's exactly why trucks are required by law to maintain much larger following distances than regular cars. And the system itself demands constant attention. Over time, moisture can collect inside the tanks, and in cold conditions, that moisture can freeze and block the lines. That's why drivers routinely drain the tanks as part of their daily checks. Compressors can wear down, and airlines may develop slow leaks. Before every trip, drivers are required to perform a full brake inspection, listening carefully to the system, monitoring pressure gauges, and making sure the compressor is functioning properly. This isn't a set-it-and-forget-it setup. It's an active system that needs regular monitoring. But here's the key advantage. Even when something starts to fail, the system still works to protect you. Because of its fail-safe design, losing pressure doesn't reduce braking power. It actually causes the brakes to apply more strongly. So here's the shift in perspective. At first, air brakes might seem like an outdated, heavy-duty solution compared to the smooth, simple hydraulic brakes in your car, but they're built to answer a completely different question. Car brakes are designed around how do we stop the vehicle. Truck air brakes are designed around what happens if something goes wrong. One system is built to perform, the other is built to protect, even in failure. And that mindset isn't unique. It's the same principle used in aircraft landing gear that locks into place even during failure. Safety systems in nuclear reactors that default to safe states without power, and even the dead man's switch on machines that instantly stop when control is lost. So the next time you hear that familiar hiss from a truck at a loading dock or a bus settling into a stop, it's not just mechanical noise. It's the sound of a system designed over 150 years ago, quietly doing exactly what it was built to do: assume the worst and keep people safe anyway.